Hello, wonderful people. Welcome to Cosmology Talks. Today we have Lucia Hackermuller, who is an associate professor at the University of Nottingham, and Mark Fromhold, who is a professor at the University of Nottingham. Today they're talking about fundamental physics in the lab and how it might help cosmology. This is really cool. I just love this stuff. Normally nowadays, if you're talking about new physics experiments, you're talking about billions of dollars or at least hundreds of millions. But there are genuine reasons to suspect that certain classes of new fundamental physics could actually show up in a lab. I mean, it might still cost $1 million to build something, but that's 100 times cheaper than 100 million. This is interesting because if it worked, then lots of labs all around the world could test it. And then we might have thousands of groups gaining new insights into this new fundamental physics. And maybe we could even get some technology from it, because if it's doing something in a lab, we could build stuff that uses these effects in lab-sized objects. But anyway, I'm getting way ahead of myself because we're just talking about possibilities. Nothing's actually been detected. But that's why I find this stuff really, really, really cool. So welcome, Lucia and Mark. Do you want to start by telling us briefly how we can constrain fundamental physics in the lab?
Yes, so the idea is to use cold atoms to detect dark holes. And in Nottingham here we have a number of experimental setups. So we work with ultracold, and there's a sample of them here. We work with ultracold quantum gases, bosons and condensates. We have an atom-photon interface, and we also work with 3D printed systems. And then we also have a fourth system where we try to make very large bosons and condensates. And the idea of this proposal is the following. So we have a chamber, and we fill that with a gas, and then we remove this gas. We do that with a certain speed. Then domain walls are formed. But the problem is that these domain walls, they form and then they vanish again, so it's hard to determine when they are actually there. And now we come up with this new idea to use a 3D printed chamber, and which means we can shape the chamber in any way we want, and we can make it such that the boundary conditions fit the domain walls and make the domain walls stick and be trapped. So we start with a new chamber, we remove the gas, and we add specific spikes that are made exactly such that the domain walls will be trapped. We then remove the gas again, and now the domain wall is trapped, and we can now test that by using an ultracold cloud of atoms. Here's the cloud, and when we drop it through that domain wall, it will be deflected. So instead of going straight, it will fall to the side.
Late last year, Kate Clements, the Clements of Clements et al. Actually gave a talk from the theoretical perspective on this exact same topic, talking about the fundamental physics that would be causing these domain walls and things. So it's a very good partner talk to this one. So if there were only two things people watching this video remember about this topic 6 months from now, what would you want them to be?
That you can use cold atoms to answer cosmological questions in the lab, and that a new approach to that is the use of 3D printed chambers, because they can be made exactly in a shape that is predicted by theory, and therefore can give an exact answer to a scientific question.
Yeah, and the interplay between physics and engineering as well. The fact that the need to make the physics robust enough to take out into the field and be an actual device meant that people needed to 3D print structures, and actually that 3D printing then allows experiments to be done to test completely fundamental physics of dark energy.
Yeah, that's interesting. I wonder what the audience of this channel would think the phrase fundamental science means, because naively I'd have thought quantum physics that is just the standard model Hamiltonian, I guess, is not fundamental because it's already well known. But I guess from the perspective of an engineer who's building things, quantum mechanics is very, very, very fundamental. I mean, it's the most fundamental thing we know. Yeah, so that type of fundamental is fueling the other type of kind of new fundamental extension of the standard models. That's cool.
One of the points that I would make would be the feedback from fundamental science that's enabled new technologies, but actually in developing those technologies, that's now enabling completely new directions in fundamental science. So there's kind of like a wheel of energy, really, whereby fundamental science fuels technology, and in turn that technology enables new fundamental science to be studied.
Cool. So why is this interesting today? What is it that is happening in 2024 that is making this possible? And what are the questions that are being solved now? And what is the background that leads us to your recent work?
Yeah, so the advances in fundamental physics that Lucia is talking about from the point of view of being able to shape vacuum chambers have really emerged from a global investment in so-called quantum 2.0 technologies. And these are distinct from the quantum technologies that we all use around us, for example, computers, the internet, microchips, lasers, MRI scanners, because whereas in those earlier quantum technologies, the ones that we're using now, so-called quantum 1.0 technologies or 20th century quantum technologies, the things that are actually doing the work are electrons and photons. In quantum 2.0 technologies, it's entire atoms that are being manipulated and being used to tell us information about the world around us and being used, for example, to sense things. So because of the emerging practical applications of 21st century quantum 2.0 technologies, there's been and is ongoing huge investment globally. So already in excess of £30 billion, $30 billion. Annually, that's around £3.1 billion already. The rate of investment in these emerging technologies is pretty much exponential. It's tripled in the last 4 years or so. So a couple of years ago, the US and the European Union have announced major investments in public funding for quantum technologies. That's also matched by industry funding. There's a big industry push now to develop real-world quantum technologies. But actually, so far, it's China that's made the biggest investment in quantum 2.0 technologies. You can see from this bar graph here showing investment made by different countries that China's at the top with an investment of just over $15 billion. Then the European Union, the US, Japan and the United Kingdom. Actually, this year, the United Kingdom's announced £2.5 billion worth of additional investment on top of the £1.3 billion that's in this table here. So these data are taken from a McKinsey & Company report, which started in 2022. That shows really the financial interest in quantum technologies, and you can see that their report, annual report's called the Quantum Technology Monitor, and that's a really useful resource for tracking how fundamental science is making its way into new products. In this case, though, from the point of view of using vacuum chambers to search for domain walls for dark energy, it's quantum technologies and emerging tech that's feeding back into fundamental physics research.
Do you mind maybe extrapolating a little bit on what the expected technological uses for because I mean I doubt that China's investing $15 billion looking for dark domain walls, so they must have some idea of something that's going to be more immediately useful. What is the sort of thing that people are expecting? Is it quantum computing sort of stuff or something else? Or
quantum computing's a big one. That's probably further from market than some of the other applications, for example, quantum sensing. So I'll talk a bit more about that later, but sensing of electric fields, magnetic fields, gravitational fields, rotation time as well, using it for really precise clocks. So very high precision timing is important for things like financial markets, which rely on people knowing exactly when trading's happened. There are secure communications as well, and I'm sure that China's interested in that, quantum information processing, quantum information sharing in a secure way. So as I've said, these emerging 21st century quantum technologies exploit far more exotic things than the electrons and photons that are in laser pointers and computers, and they tend to use the quantum behavior of entire atoms, either the internal electronic structure of the atoms, or sometimes, as Lucia will describe later, giant quantum waves that are formed when we cool atoms to within a few billionths of a degree, or also of absolute zero, the lowest possible temperature. So these giant quantum waves are made by cooling atoms, almost always alkali atoms, to below a millionth of a degree, a few billionths actually of a degree above absolute zero. So it's a really interesting question about how these atoms are cooled, and to think about how we might cool atoms to those really low temperatures. It's useful to think about what goes on in a kettle when we put energy into that and heat things up. So when we heat water in a kettle, we speed up the water molecules, make them move fast enough that they can actually escape from the water and form steam. So we can think of heating things as being equivalent to increasing their speed, and therefore, conversely, we can cool atoms by slowing them down. So taking them from the very fast speeds that they're moving around all around us in the air at the moment, and taking them down, slowing them down literally to a snail's pace. So just to describe a little bit about how that's done, the cooling is done using a so-called magneto-optical trap. So it's really a fridge that's made just of magnetic fields and light, photons in laser light. On the left here you can see one of these magneto-optical traps, a refrigerator for atoms made of light and magnetic fields. You can see coils in there, two copper coils towards the right hand side of the picture. They create the magnetic fields that can be used to trap the atoms, and also some of the cabling in there is feeding into lasers that are used to slow the individual atoms down and therefore cool them. So the lasers slow the atoms down, and then the magnetic field also helps with that cooling process. So just thinking a bit about how cold these laser and magnetic field cooled atoms are in terms of how close they are to absolute zero. So I've put a thermometer on the screen here. You can see right at the top of the temperature scale, around 1,000,000 Kelvin. That's the temperature inside a tokamak fusion reactor. Solar temperatures, the surface of the sun's around 6,000 Kelvin. Of course, the melting point of water is 273 Kelvin. And laser cooling will slow atoms sufficiently to make the temperature of a gas of those atoms just around a millionth of a degree or so above absolute zero at minus 273 degrees Celsius. By using magnetic fields and a process known as evaporative cooling, which is exactly the same sort of physics that explains why your coffee cup cools when hot water molecules escape from the coffee, leaving behind the slower moving, cooler water, then by using this process of evaporative cooling, it's possible to cool down to just 1/10,000,000th of a degree above absolute zero. And those really incredibly low temperatures I find mind-blowing. I still find it quite remarkable to think about how cold that is. And I found it quite useful to think in terms of a distance analogy for temperature, just to really emphasize how close to absolute zero a few billionths of a degree above absolute zero is. So if we think of a distance scale on this Google map here, from New York on the left to where I am sitting now in Nottingham, that's around 5,500 kilometres. And if we were to imagine a giant thermometer spanning that gap, and we were to say that New York was at room temperature, Nottingham was at absolute zero, then 1/10,000,000th of a degree above absolute zero on this distance scale is just the width of a blood cell, a red blood cell, from my office door. So that just gives an indication of how very close to the lowest possible temperature these fridges made of magnetic fields and light go.
I remember something that someone who was talking about one of these laser cooling kind of experiments said that I found amusing once, which was, even though the hottest place in the universe is probably in some very explosive thing, maybe around a black hole or whatever, the coldest place in the universe, if there's no other intelligent life, is probably on planet Earth.
It's true. I mean, it's many orders of magnitude colder than the temperature of outer space. So for sure, it's the coldest temperature ever created, and probably that's ever existed so far. So just to think a little bit about what that reduction of temperature means in terms of the changing speed of atoms in the gas as they're cooled with the lasers and magnetic fields. If you think about the atoms and molecules in air now at room temperature, they're moving around the speed of a jumbo jet, an A380 I guess it would be now, bit of an old-fashioned photo that really. If we cool things down with a laser to a millionth of a degree above absolute zero, the atoms then are slowed so they're moving around the speed of a mosquito. But actually, if we use evaporative cooling to go below the limit that can be achieved by lasers alone, and go down to 1/10,000,000th of a degree above absolute zero, the atoms are literally moving at the speed of a snail. And it's in that regime where individual atoms lose their identity and they merge together quantum mechanically and act as a giant quantum wave, which is approaching the millimeter scale, so it's almost big enough to see with the naked eye. So this kind of cooling process is taking quantum mechanics from the atomically small domain where we think of it traditionally and making it something macroscopic that is pretty certainly large enough to see with an optical microscope. So that slowing process and that loss of identity, that creation of a giant quantum wave, makes a new state of matter that's known as a Bose-Einstein condensate that was first realised towards the end of the 20th century, but is now starting to be used in 21st century technological applications.
Cool, thanks, Mark. That's awesome that these insanely cold temperatures can be achieved. Let's maybe now go into some of the physics about how this works. How can we cool atoms so much in the lab?
So how do we actually do this? This is the apparatus that stands in the lab and that has a length of 2.5 meters. And in our system we use lithium-6, which is a metal, and we heat it up in this oven over there, and then it flies at high speed and is first slowed down in this thing which is called the Siemens slower, and we then shoot our photons on our atoms in the magneto-optical trap. This is really the heart of the experiment. With that we reach a certain minimum temperature, and then we load these atoms in a so-called optical dipole trap. These are the violet lines that you can see here, and that is the main experiment. So what we do is we use the two lowest energy states of lithium-6 that gives us a spin up and a spin down atom. They are then combined into a molecule which has spin 0, and these molecules can condense. This is a picture of the lab, including a PhD student. So these are big experiments, not as big as CERN. This all fits into a room, but still one needs a large vacuum chamber, one needs high currents and controls. In the insert here you can see this magneto-optical trap, including the coil that makes the magnetic field, and the lens for the optical dipole trap. So this shows you our laser system when the light is on. So lithium-6 has a resonance at 670 nanometers, so that is very well visible and very red. Therefore all this red light that you can see here, also lots of optics that we need, mirrors and beam splitters.
Can I just ask a super dumb question about those pictures? So when you show the kind of toy diagram about how things are working, you have one laser beam, and then when I, as a theorist, cosmology theorist even, haven't been in a lab since I was an undergraduate student, see a photo like this, it's just, why are there so many beam splitters and so many mirrors? Didn't you just need one beam, one laser? Like, why is this all necessary?
It's a question that actually many people ask, so you're not alone. Well, because the picture that we tell you is a bit oversimplified. So first we say an atom has only 2 energy levels and then it scatters photons, but actually for lithium there are 3 energy levels, so we need 2 lasers in parallel that do the same job. Then we need to stabilize our lasers, meaning the atoms, they have their lines and they are so picky that they want one exact wavelength. So we need to fix our laser at that wavelength, and it's so precise that we would need a very expensive wave meter all the time, or we do something that's called spectroscopy, meaning we take a hot gas and then we measure what comes through the hot gas and we can see the resonance, and then we can fix our laser there. So half of that table is to fix those laser frequencies. And in total, there are actually 3 lasers here, 2 for this cooling process and 1 for imaging when the cloud is finished, for taking a picture. And then the other half of the table is distributing the light, because yes, in a 1D picture, you just have 1 laser beam and an atom, and that's scattering the photons. But in reality, you live in the 3-dimensional space, so you need at least 2-3 laser beams coming from both directions, so that makes 6 beams, and then in addition you have a slower beam that's 7 beams. So, and all of those are coupled here into optical fibers and then go to another optical table. So this is like 2 meters, and there the actual experiment happens. So this is why it's so big. But of course, with respect to quantum technologies, we do try to make things smaller. I think I have a slide where one can also see a more compact system, but there's some technological development in order to make it compact and stable and robust.
Yeah. Yeah, I mean, you compare the first computers that were the sizes of buildings to modern cell phones. Once something is shown to work, you can work on doing it more efficiently. Yeah, cool. Thanks. That's a very satisfying answer.
Yes. So here we make a cloud of cold atoms in the lab, and you can see the coils that make the magnetic field, and you can also see the scattered red light that we need to be resonant with lithium. And then we just start the experiment. You can also hear the lab is noisy, and then in the center here you see there is a cloud of atoms being trapped, and so it's shaking a little bit. And when we switch off the light, then it's not held anymore, it's gone, it drops. And then we switch it on again, the cloud loads, and here it's hovering in free space. And if you have not been in a cold atom lab, then this is possibly the coldest thing you have seen so far. This has a temperature of 300 microkelvin, and this about 10 to the 9 atoms. So after this step where we shoot our photons on the atoms, we have to cool them further, and this is the evaporative cooling that Mark has already mentioned, which works in exactly the same way as the coffee cup, the mug of coffee. So we load about 10 to the 6 atoms in our mug. In our case, this is a crossed dipole trap, so these lines that you can see here, this is a laser beam, a very strong laser beam with power of 100 watt. And we focus this laser down to the diameter of a hair, to 90 microns. And then the first step is we really hold our atoms in our mug, and the hot ones manage to escape, and the ones that stay in the mug need to redistribute the energy, and that makes them in total colder. And in this picture you see the cloud has shrunk, the wings have left, these were hot atoms, so this is a much colder cloud now. And then we also lower the walls of the mug, and more atoms can escape, and the atoms that are left are forced to become colder and colder and colder. And with that we can go down to temperatures far below 1 microkelvin, and that corresponds to 0.1 T over TF, and we have 100,000 atoms in these clouds.
Did you define TF at some point and I just missed it, or what is TF?
The Fermi temperature.
Okay, of that group of atoms.
Yes, exactly. Maybe it's better if I say it's 10% of the Fermi temperature.
Do you want to give a maybe one sentence, if you can do it in one sentence, explanation for those who maybe have never encountered laser cooling before? Because you were talking about a 100 watt laser beam cooling the lithium. I guess to someone who's never encountered laser cooling before, you know, if I've got a 100 watt light bulb, it's certainly not cooling something, it's heating it up.
The 100 watt laser forms our mug, and what is important here is that this laser is not resonant, meaning it runs at a completely different wavelength, and therefore the atoms do not absorb this light. They see the potential, the dipole potential formed by the laser, but they don't scatter the photons, or they scatter only very few photons. And therefore, although there is a deep potential that they have to sit in, very steep walls, but they don't heat up. So here one can bring again the analogy of the coffee mug. So your coffee cools when it sits in front of you, right? And how far does it cool down? Well, it cools down to room temperature, but not further. And why is that? Because it cools down, and at the same time it's heated by the environment. And the same is true for our mug. It cools down to the temperature of the environment, and the temperature of our environment is very cold. And this is exactly why it's so cold, because so few photons are scattered out of this mug. It does not really interact via scattering, only it feels the potential. And the potential is called the dipole potential. So you might have seen dust particles that are trapped in rays of sunlight, or also smoke fume particles are sometimes trapped, and this is exactly the same force. The strong field can create a dipole potential for particles.
Okay, I was familiar with the laser cooling idea of dipole potential. I did not know that. Well, I'm having a discovery moment here. Are you telling me that that rays of light, like from like a hole in the curtain or whatever, or hole between the curtains, dust gets trapped in that beam? I thought it was just that you could only see the dust that was in the beam, but that dust somehow feels a potential because of the light, because of a temperature gradient that it causes in the air or something, or how does that work?
So the advantage of the dust particles is that they are very big. So the dipole depends on the size of the thing. So therefore the dust particle has a huge dipole moment. So there's also this experiment that teachers quite often do in school. You create some smoke and you have a laser pointer, and then you see the smoke in the laser pointer, and this is the dipole force. So although this trap is very weak, because these large particles have a huge dipole, they might not really be trapped, but they are attracted, and then they're just moving around the beam and along the beam. Yeah.
There's a potential well
It's a potential well, exactly.
Yeah. Oh wow. Okay. Cool. I didn't know that.
So we detect the BC by measuring the velocity distribution. That means by just dropping the system. And when it's hot, we still get the Boltzmann distribution. That would be the first picture. The temperature the system is not condensed. The system is very hot. When we approach the condensation temperature, we see that there is a little peak forming. We move away from this Gaussian distribution, and when we are far below the condensation temperature, we get this very sharp spike, meaning all atoms move with the same velocity, but they still have a starting distribution, so they drop like a stone almost. And below here, we can see the cut through these clouds. You can see the colder we get, the more spiky they become, and in the end, there's only a very small thermal cloud there, and on top of that sits the Bose-Einstein condensate.
So what's the difference between the condensed part and the thermal part? Is just the background that hasn't reached that lower temperature, is that right? Okay.
Exactly. So there is almost always a thermal cloud around the condensate that exchanges interactions with the condensate.
And more of the particles are in that thermal part than the condensed.
No, that depends on how cold the system is. So below the condensation temperature, you can see the yellow cloud. This is far into the condensate. There is only a small addition of thermal cloud. The little mountain here is the thermal cloud, and the big spike, all of that is the BEC.
Yeah. So earlier you asked what the use of quantum 2.0 technologies is, and one big application area is in sensing. So there's a whole range of different forces and fields that can be measured by using the wave-like behaviour of the ultracold atom clouds to figure out what forces are acting on those clouds. And if you bring, for example, two Bose-Einstein condensates together, you see a very rich pattern of interference fringes, maxima and minima in the atom distributions, which is very analogous to the way that two laser beams that pass through double slits would diffract and interfere with one another. So by looking at the wave behaviour of clouds that are interacting with one another, it's possible to measure the forces that are acting on those clouds. And so just some examples of the forces that are being measured or can be measured by using cold atoms and indeed sometimes thermal atoms too. One application area is rotation, so making a gyroscope and accelerometer that can be used to figure out where a person is or where a vehicle is without needing to have some kind of reference to an external system like a satellite in the case of GPS. So in other words, signal-free and therefore jam-proof navigation systems that can work underground or inside a building, but which are not susceptible to jamming by people that may want you to not know where you are in the world. Another force that there's a lot of interest in measuring using cold atom systems is gravity, and the reason for that really is underground mapping. So by measuring variations in gravity as the centre moves over the surface of Earth, it's possible to do really sensitive environmental studies. So, for example, measuring the thickness of the permafrost to look for climate change effects, but also looking for natural resources like water in aquifers and minerals and so on underground. There's interest as well in using cold atom sensors to look for archaeological remains underground, but also pipes and infrastructure in underneath urban streets. So this is what's underneath a street, typical street, and you can see that there's all sorts of pipe work there, electrical cables, sewers, internet cables. So the underground under our streets is incredibly congested, and that's one of the biggest risks to big infrastructure projects, because people just don't know where it's safe to actually dig. If you're going to start digging up the road, you don't want to go through a utility pipe or electric pipe or anything like that. And actually recently in Nottingham we had a new tram system that opened, and that tram system was delayed by many months because people didn't know where to drill, and they thought that utility pipes that were on one side of the street actually were on the other side. So this is a couple of Nottingham trams. The one on the right there is named after Sir Peter Mansfield, who was a Nottingham physicist who developed magnetic resonance imaging scanners. And actually his work on MRI scanners was enabled by work that was done on the other side of town 200 years ago by a guy called George Green, who was a miller by day, but by night developed green functions, which were used to develop MRI scanners, and which now we're using to develop quantum 2.0 or 21st century technologies by using green functions to gain really precise control of magnetic fields for reasons that I'll come back to. Final application of quantum sensors that I'll mention is magnetic field sensing. There's big interest in Nottingham and increasingly globally in using atomic sensors to measure the magnetic fields that produce around our brains, and so image what's going on in the brains of people that are moving around and crucially interacting with one another. So that's a big area of application in neuroscience of quantum 2.0 sensors.
Okay, so now let's move to the 3D printing part of things. One thing that we have made is a 3D printed UHV chamber. This is the world's first 3D printed chamber, and in the UHV. And the big advantage is that we are not limited by any thing that we can do mechanically. We can make any design. So here we have made this part that was used to create, again, a cloud of cold atoms, a magneto-optical trap, and we just built it such that it does the task. So we defined, okay, we need a certain number of windows, and then we just made a thin skin to the vacuum, and we filled the area around that with this type of foam to give it stability. And at that point we also didn't know whether that would work, because 3D printed surfaces are rough, and rough surfaces you don't normally want in UHV systems. But lucky enough it did work, and we could reach 10 to minus 10 millibar of background pressure, which is really good after only a short baking time. And I also have one of these chambers here, and they're really lightweight. I can throw them around. I could not do that with a normal stainless steel chamber.
What is the actual compound? What's the material it's made of?
This is aluminium, silicium, silicon, magnesium. Sorry, it's late. It's called Al-C10Mg, and that is a cast compound. But we also later printed titanium. So here you can see the fully mounted chamber. So we closed it up with standard parts, and then in order to measure the pressure that we can reach in this chamber. So you can see here again it's Al-C10Mg. It has a weight reduction of 70%, so it's just 30% of the weight that a normal chamber would have. In another application are these modified surfaces that we are currently looking at. So this is now in titanium 6.4, and we print these spikes, for example, that would also be used to detect the dark holes, or we can also print this honeycomb pattern. And one of the interests why we do this specifically is because we want to make now an artificially rough surface and to coat that with a non-evaporative getter, a neck coating, and this neck coating acts like a kind of glue such that particles can stick on it, so this can work as a pump. And by modifying the surface, we can massively increase the surface. So these small elements can pump our vacuum chamber. We can also put that on the full inside of our vacuum chamber.
So we'll say a little bit now about the parts that are needed to make these quantum 2.0 technologies. You've already heard from Lucia about how to make ultra-high vacuum chambers that are used to keep the atoms cool and stop them being hit by faster moving atoms all around them. We also need to make laser systems and vapor cells, containers that hold the atoms whilst they're being cooled. But in the next bit, I'll just say a bit about magnetic field shaping systems that are needed both to cool the atoms and trap them, but also to shield them from the effects of Earth's magnetic fields. So we make magnetic shields which are used to get rid completely of Earth's magnetic field, so that if you're measuring, say, gravity, your measurements are not messed up by the influence of Earth's magnetic field on the wave behaviour of the atoms and of electrons inside those atoms. So as part of developing a fridge for atoms based around the 3D printed ultra-high vacuum chamber that Lucia has described, that we call the sea urchin, because when we looked at it, we thought that the texture on the surface that you can see there looked a bit like a sea urchin without its spikes. So that created the bag in which atoms could be held while they were cooled with lasers. But we also needed to integrate with that setup a magnetic field generating system that would give the magnetic field bit of the fridge. And we did that by taking ferromagnets that we bought online from Amazon for about £10 and figuring out how to hold them in a 3D printed former around the chamber. So on the right hand CAD diagram there, you can see two blue discs, and in there you can see a series of circles. Each of those circles is a hole into which we pushed a ferromagnet, and we used the green functions developed by the Nottingham Miller to figure out where to put those magnets in those holes in order to create exactly the right shape of magnetic field for cooling the atoms. So the laser cooling system here used magnetic fields that were developed by permanent magnets. That meant that it's consuming no power, so we don't need to put an electrical current through an electromagnet here, and also the assembly was very low cost. So that of course helps to develop technologies that are scalably producible and cheap enough eventually for people to buy. So we've done a lot of work on developing really high precision magnetic field generating systems that will generate the kind of biases that you need to cool atoms, but also to shield them from Earth's magnetic field. So this is a shield that we've developed in collaboration with a company, Magnetic Shields Limited in Kent, in the southeast of England, and it contains inside the bore of that shield a series of flexible PCBs, so 9 flexible PCBs that wrap around on the inner side of the cylinder, and the tracks on those PCBs are chosen to generate really precise magnetic field components along X, Y, and Z, and field gradients and curvatures as well, taking into account the coupling between those PCBs and the cylinders, which are really high permeability, magnetic permeability.
What is a PCB?
Printed circuit boards, sorry, yeah. And so we designed the shapes of the tracks on those printed circuit boards by using Green's functions that were developed on the other side of town 200 years ago by George Green. So it's kind of nice that his work fueled MRI development in Nottingham, and now we're using it further for 21st century quantum tech. So thinking about the 4 key parts of quantum technologies, we've covered the vacuum chamber and the magnetic shields. Laser systems, in particular vapor cells, which are the containers of the atoms that eventually are cooled by the lasers and the magnetic fields, are important. And Lucia is going to talk about very recent work that's been done here in Nottingham on developing those vapor cells.
So we also print this vapor cell. We did that recently, and we find that quite exciting. These cells are actually tiny. I don't have one here, but they're about 5 millimeters in size, and we can use them to put atoms in to do spectroscopy, and again to use them for quantum technologies. The big advantage, again, this is the first time that such a thing has been printed. The big advantage of the printing process is, again, that we can have freedom in design, so we can make structures now that were impossible to make before, like the one in the middle. This is this twin cell. We also could make kind of a snake, such that we can have a large optical path through that cell. And it's also important to demonstrate that the optical quality is good enough, that these windows are flat enough, that the laser beams are not much disturbed by the printing quality. And we can show this. So in the upper figure, you can see that there's a red beam, the green beam, and they pass through not that much disturbed, so good enough to do some measurements. And in addition, we can also print other materials on top of this glass. So in the lower right corner, you see now printed graphene directly on the glass, and that can be used as a temperature sensor or as a photon detector. So we can print graphene layers together with silver. The silver makes the contact, and then this can directly detect photons on the printed cell. And here on top, you see we mounted it to a vacuum chamber in order to be able to fill the cell with atoms. And you also see here, now we shine resonant light that the atoms can scatter through the cell, and you can see this bright beam that is the fluorescent beam when we irradiate the atoms with the resonant light. And we can do this typical spectroscopy. So here we vary the wavelength of our laser, and we see the exact transitions. These are the transitions of the atoms. So they are distinct. That shows that it's a rubidium atom, in this case rubidium-87 together with rubidium-85. And then we can also use that to stabilize a laser. So that's a first application. So this is a very small reference cell, and this is the quality of the blue line. It's called Allen deviation, that shows the quality of the laser, or of the lock, of the stabilization of the light, to using this tiny printed vapor cell. Then we also make these lasers much smaller. So you saw the big optical table with all the optics. Now we try to make that as compact as possible, and that has several advantages. So here, this white frame is a printed frame, and we have made the design such, what this one does, it stabilizes the frequency and distributes the light. So it's basically the same as you have seen before for the lithium setup. This was about a square meter, and this is now about 8 by 6 centimeters, this frame, and does the same job. And the advantage is, again, we can design it very compact. That also means we actually need less optics, because we don't need to be so accurate anymore. We don't need so many degrees of freedom anymore. So we have, on the one hand, we have fewer degrees of freedom, that makes it more stable, and we also don't need them anymore because our paths got much shorter. So the task got a little bit easier, if you want. So this is this power distribution and stabilization system. This is DFB laser diodes, a laser diode in a printed mount, together with a printed isolator, or an isolator mount here, such that the light only goes out in one direction, and that can also be connected to an optical fiber. And the material that we've used here is called PMMA, and that is a plastic that is reinforced, glass fiber reinforced plastic, that is quite stable and has a low thermal expansion coefficient. Another application of our 3D printing is, so the chamber that I showed you before was really the first demonstration that this can work for vacuum chambers. And here now we have a real application. So we designed and printed a chamber that's meant to go to space at some point. And so this will be a full gravimeter, an atom-based gravimeter, sitting in this then combined vacuum chamber printed out of titanium-64.
So if you're putting something in space, is that still of a Bose-Einstein condensate of atoms? And then does it have to be made and then sent into space, or can it be kind of made remotely in space? Or
no, it is made remotely in space. Yes. So because the Bose-Einstein condensate is not you make them once and then they live forever. They would have, because they live in vacuum and they live in their laser trap, but they do still scatter background atoms and photons. So you lose them. They have lifetimes of, I think the longest lifetime that I know of is about 300 seconds, but normally they have lifetimes of 40 or 100 seconds, and then it's just scattered too many particles. So there is currently a cold atom system on the ISS that is at the moment used. And the advantage of our methodology of the chambers is that they can be much more lightweight, and also the systems can be much more compact, because you can make the design much more compact. As in the laser system, we can go from this 1 square meter size table to a very compact box that does the same thing. Similar, not exactly the same, but similar for the vacuum chamber. We can make it much more compact and smaller. And on this slide, so here we used again our originally printed chamber that is sitting here. And this whole system now is a magneto-optical trap that makes a cloud of 3 times 10 to 8 atoms. This is the white thing that you can see here. Again, rubidium atoms. And so not a BSC, it's just the first cooling step where we scatter photons using all these printing methods. So the stabilization and light distributions, the printed laser mounts, and the printed chamber together with outcouplers. And I also have that system here. So, and also there are Mark's magnets that he described earlier that create the magnetic field to trap the atoms. And the white things that you can see, they are really just there to hold the optics. The outcouplers here go the fibers that create the light that trap the atoms in the center.
So is the University of Nottingham the kind of cutting edge of 3D printing to do these things? Are there any other groups 3D printing the chambers, or is it just you? Were you the first? Or
there are other groups around the world doing 3D printing, but we were certainly the first to print a UHV chamber, because it was not even clear whether that would work at all. In Birmingham, there was a printed flange done before us, and I'm not aware of any other groups printing chambers right now. The same is true for the glass. There are several groups that print glass in different quality, but there is no group that prints vapor cells that have a high enough quality to be used for quantum technologies. Also, a specific application of the glass cells can be a very compact magnetometer, as Mark showed, for example, for brain activity detection.
I said at the beginning that typically new fundamental physics research costs hundreds of millions or billions. I suppose the reason that other groups aren't also 3D printing is presumably the 3D printer costs quite a bit of money, and running it with its equipment costs quite a bit of money as well. Are we talking like a few $1 million in this case, or?
You can buy metal printers now for about $500,000, that kind of commercially, but there's a lot of expertise in making the support structures around these 3D printed systems such that heat from the metal as it's being printed doesn't actually melt other bits of it. So there's a lot of expertise goes into the kind of heat guiding and heat management needed to make a structure and to have it mechanically robust as well. So it's kind of got to be held up with props, but those props have also got to be pretty good at conducting heat away. So it's much more technically demanding and requires a lot more skilled engineering than you would think. It's not like the kind of 3D printing that you got in your living room because of the temperature and the materials that are being printed.
Yeah, so where to next with this? I mean, from the cosmology side, I guess people watching this might be most interested in the dark domain wall side of things, because as I said, Kate gave this talk from the theoretical perspective of what models this would be potentially finding. Now I'm talking to you guys, the experimentalists. What is the obstacle to building this and finding or ruling out these models tomorrow, like or 6 months from now? What do you need to do it? You have the 3D printer. I mean, I'm asking a very naive question of, like, I'm sure there are lots of complications. What are they?
No, we don't think that from the experimental side there would be that many complications. So it's really a matter of designing the spikes and printing them and putting them into the system. So I think it's also very appealing here that a clear yes or no answer should be relatively easily achievable, because the prediction is clearly that the cloud is deflected. So and it's so much deflected that we can for sure measure that. So we are in the process of building it up, of creating the design and implementing it in our existing lithium system. And there are of course other projects that we're operating. So we need to find the time. We need to find enough research funding, students, postdocs, and so on, who can work on that full time.
I see. So just, another sort of naive question. You say enough research funding. The actual printing is, now that you've got it set up, as Mark said, that you need to train the expertise to make sure it's not breaking itself as it builds it. But is the actual materials cost not the significant thing here? It's the people, labor cost of designing exactly where to have the spikes, having the expertise to build that with the 3D printer and not breaking it, and then setting everything up. Is that where the actual kind of problem is?
Yes. So the chamber is not exactly cheap, so it's still the material is costly and so on, and depends also whether we have that printed in-house or we outsource it to a company and so on. And of course we also need to design the experiment carefully, so have a large enough field of view, make sure we can have a good repeatability where we exactly create the cloud. But one of the advantages of the scheme is also that we can do a differential measurement, so we can do one shot where we pump out the gas such that the dark walls should be formed, and in the next shot we can not do that, not pump out, and then or prepare the system differently, and then we would not expect any walls, and then we can compare the two measurements. So if there are any external influences like magnetic fields or electrical fields, they should be cancelled by this differential measurement, differential approach.
Cool. And do you have a kind of feeling of a timeline, or does this actually depend on winning or not winning funding through grants and things? Like, would it be, if I was to talk to you in 12 months, would we have a result, or 24 months, or
possibly rather 24 than 12? So it depends on winning the funding, and from that point, I mean, we can do that relatively quickly, and it also the costs are not massive, but still we need a bit of time to implement it. We need to change our central chamber of our cold atom system to that chamber that has the printed part. We need to build up or enlarge and improve our detection systems. So that does take about a year. Yeah.
And I guess one last question I would have in the kind of future sort of thing. Do you or your cosmology collaborators in Nottingham or outside of Nottingham, do you have other ideas other than these domain walls that might be on the horizon that we might be hearing about, even only on the kind of theoretical kind of side of, like, this is something we could do? Are there other things kind of simmering away in the background at coffee discussions in Nottingham?
I think for the cosmology question, would probably be best to ask Claire. What we are also doing, this is this experiment number 4. We're trying to make atomic clouds that are really massive. So that means in the standard mod, we make about 10 to the 8, 10 to the 9. We have developed a method where we think that we will be able to push that to 10 to the 11, 10 to the 12 atoms, and then there is a prediction that we should enter a regime where we have a quantum system that has so much mass that also the gravitation becomes relevant, and we can at least get closer to a regime where quantum gravity could play a role. So we're really only taking the first steps, but the idea is to take a cold atom system and make it as massive as possible, and then see whether that is good enough to measure some effects of quantum gravity.
Okay, quantum gravity, I guess, again has different possible meanings, because normally when you think about quantum gravity, you think about very, very high space-time curvature kind of regimes. But I guess what you mean here is that you would be measuring the gravitational field of a system that is in a very pure quantum state, whereas normally, like, the Earth is not in a pure quantum state, and we can measure its gravitational field.
The idea is to make an interferometer superposition state, so something that's a clear quantum effect, and actually make two of those, and then one interferometer, because of its mass, would disturb the other one. So they would only couple through gravity, but the coherence would be lost, the quantumness would be lost through that gravitational coupling.
Is there anything that one would expect that's mysterious there that isn't just described by a kind of gravitational field in a quantum system?
The big unsolved question is, can space-time be in a superposition or not? And that would I don't want to say resolve, because this is also, I don't know whether this can happen on a time scale of 50 years or so, but this is a question that we have to look at some point.
Yeah, I guess if it wasn't I'm just speaking as a kind of naive person who's not 50 years in the future and knows the answer to this, but if it was in a superposition, that would be what I would expect, and it would be the kind of, it's good to tick that box, but it's not that mysterious. But the very interesting thing, I guess, would be if it couldn't be in a superposition, because then it's different to everything else. Like, you can put the electromagnetic field in a superposition.
Exactly, it will be different to everything else, but also if it is in a superposition, that's also quite weird. Because that would in a way mean that also trajectories can be in superposition and time can be in a superposition, and things like that.
So I was going to say, one thing that would be really cool to do within this sort of system would be to look at what happens if a BEC interacts with this domain wall, because currently the predictions have been for a single atom traversing that domain wall. We know that BECs, if they encounter sudden changes in potential energy, can have dramatic things happen to them, like they can explode on reflection and things. And so it'd be really interesting to see what happens when a multiple atom system interacts with either one domain wall or maybe a whole series of them. So there's a lot of cool dynamics that could happen there, I think.
Oh, that seems like a very cool thing. If you're a cosmologist with a little bit of a background in atomic physics, that might be a cool research project. You should read Clements et al. And see what would happen if it was a BEC and multiple domain walls. That would be very exciting. Cool. Well, the last question I normally ask is, what work being done in cosmology at the moment do you think is particularly interesting but underappreciated? Given that neither of you are cosmologists, you might not know enough about cosmology to answer that question. So I'll maybe turn it around a little bit. What work being done in cold atoms, it doesn't have to have any relevance to cosmology, do you think might be interesting but underappreciated by the broader community of physicists?
Yeah, I mean, the big appeal of the cold atom system is and was that it can act as a model system, that we have this quantum system which is well understood and well controllable. And I think this is also why it lends itself for cosmological tests. But at the same time, there are many exciting things in condensed matter, modeling condensed matter systems, modeling transport of hotter and colder systems.
I was going to say that it would be absolutely beautiful to create hybrid systems where you have an atom near a solid state system, where the electron in the atom, one of the outer electrons in the atom, is actually shared with the condensed matter system, so that you could entangle an atom with a solid. Because some really excited atoms, Rydberg atoms, have got sizes that are very comparable with quantum dots, the kind of things that we're seeing now in TV screens. And so actually having a hybrid system where you've got a quantum dot, which is an atom, linked to a solid state quantum dot, will be remarkable new kind of testing ground for quantum theory, maybe also useful. So I'd love to see those hybrid systems developed.
Cool. Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos when they come out, and click like to help with the YouTube algorithms, both for you and the channel, because YouTube will know to recommend more stuff like this to you, and share the channel with colleagues. If you have any questions or suggestions, leave a comment. And otherwise, check out Kate's video from last year, which should be on the screen at the moment. And thank you, Lucia and Mark, for the great talk.
Thanks, Sean.